a WikiVidi Documentaries production. Don't forget to like and subscribe. Enjoy. Dead reckoning. In navigation, dead reckoning is the process of calculating one's current position by using a previously determined position, or fix, and advancing that position based upon known or estimated speeds over elapsed time and course. The corresponding term in biology, used to describe the processes by which animals update their estimates of position or heading, is path integration. Dead reckoning is subject to cumulative errors, advances in navigational aids that give accurate information on position. In particular, satellite navigation using the Global Positioning System have made simple dead reckoning by humans obsolete for most purposes. However, inertial navigation systems, which provide very accurate directional information, use dead reckoning and are very widely applied. By analogy with their navigational use, the words dead reckoning are also used to mean the process of estimating the value of any variable quantity by using an earlier value and adding whatever changes have occurred in the meantime. Often, this usage implies that the changes are not known accurately. The earlier value and the changes may be measured or calculated quantities. The term dead reckoning was not originally used to abbreviate deduced reckoning, nor is it a misspelling of the term dead reckoning. The use of dead or deduced reckoning appeared much later in history, no earlier than 1931. In contrast to dead reckoning, appearing as early as 1613 in the Oxford English Dictionary. The original intention of dead in the term is not clear, however, whether it is used to convey absolute, as in dead ahead, reckoning using other objects that are dead in the water, or using reckoning properly, you're dead if you don't reckon right, is not known. Errors. Dead reckoning can give the best available information on position, but is subject to significant errors as both speed and direction must be accurately known at all instants for position to be determined accurately. For example, if displacement is measured by the number of rotations of a wheel, any discrepancy between the actual and assumed traveled distance per rotation, due perhaps to slippage or surface irregularities, will be a source of error. As each estimate of position is relative to the previous one, errors are cumulative, or compounding, multiplicatively or exponentially. If that is the correlationship of the quanta, the accuracy of dead reckoning can be increased significantly by using other, more reliable methods to get a new fix partway through the journey. For example, if one was navigating on land in poor visibility, then dead reckoning could be used to get close enough to the known position of a landmark to be able to see it before walking to the landmark itself, giving a precisely known start point, and then setting off again. Localization of mobile sensor nodes. Localizing a static sensor node is not a difficult task, because attaching a GPS device suffices the need of localization. But a mobile sensor node, which continuously changes its geographical location with time, is difficult to localize. Mostly mobile sensor nodes within some particular domain for data collection can be used, i.e., sensor node attached to an animal within a grazing field or attached to a soldier on a battlefield. Within these scenarios, a GPS device for each sensor node cannot be afforded. Some of the reasons for this include cost, size and battery drainage of constrained sensor nodes. To overcome this problem, a limited number of reference nodes within a field is employed. These nodes continuously broadcast their locations, and other nodes in proximity receive these locations and calculate their position using some mathematical technique like trilateration. For localization, at least 3 known reference locations are necessary to localize. Several localization algorithms based on sequential Monte Carlo method have been proposed in literatures. Sometimes a node, at some places, receives only 2 known locations and hence it becomes impossible to localize. To overcome this problem, dead reckoning technique is used. With this technique, a sensor node uses its previous calculated location for localization at later time intervals. For example, at time instant 1, if node A calculates its position as loca_1 with the help of 3 known reference locations. Then, at time instant 2, it uses loca_1 along with 2 other reference locations received from other 2 reference nodes. This not only localizes a node in less time, but also localizes in positions where it is difficult to get 3 reference locations. Animal navigation. In studies of animal navigation, dead reckoning is more commonly known as path integration. Animals use it to estimate their current location based on their movements from their last known location. Animals such as ants, rodents, and geese have been shown to track their locations continuously relative to a starting point and to return to it, an important skill for foragers with a fixed home. Marine navigation. In marine navigation, a dead reckoning plot generally does not take into account the effect of currents or wind. Aboard ship, a dead reckoning plot is considered important in evaluating position information and planning the movement of the vessel. Dead reckoning begins with a known position, or fix, which is then advanced, mathematically or directly on the chart, by means of recorded heading, speed, and time. Speed can be determined by many methods. Before modern instrumentation, it was determined aboard ship using a chip log. More modern methods include pit log, referencing engine speed against a table of total displacement, or referencing one's indicated airspeed fed by the pressure from a pitot tube. This measurement is converted to an equivalent airspeed based upon known atmospheric conditions and measured errors in the indicated airspeed system. A naval vessel uses a device called a pit sword, which uses two sensors on a metal rod to measure the electromagnetic variance caused by the ship moving through water. This change is then converted to ship's speed. Distance is determined by multiplying the speed and the time. This initial position can then be adjusted, resulting in an estimated position by taking into account the current. If there is no positional information available, a new dead reckoning plot may start from an estimated position. In this case, subsequent dead reckoning positions will have taken into account estimated set and drift. Dead reckoning positions are calculated at predetermined intervals, and/or maintained between fixes. The duration of the interval varies. Factors including one's speed made good and the nature of heading and other course changes, and the navigator's judgment determine when dead reckoning positions are calculated. Before the 18th century development of the marine chronometer by John Harrison and the lunar distance method, dead reckoning was the primary method of determining longitude available to mariners such as Christopher Columbus and John Cabot on their transatlantic voyages. Tools such as the traverse board were developed to enable even illiterate crew members to collect the data needed for dead reckoning. Polynesian navigation, however, uses different wayfinding techniques. Air navigation. On May 21, 1927, Charles Lindbergh landed in Paris, France after a successful non-stop flight from the United States in the single-engined Spirit of St. Louis. This aircraft was equipped with very basic instruments. He used dead reckoning to find his way. Dead reckoning in the air is similar to dead reckoning on the sea, but slightly more complicated. The density of the air the aircraft moves through affects its performance, as well as winds, weight, and power settings. The basic formula for Doctor is distance speed x time. An aircraft flying at 250 knots airspeed for 2 hours has flown 500 nautical miles through the air. The wind triangle is used to calculate the effects of wind on heading and airspeed to obtain a magnetic heading to steer and the speed over the ground. Printed tables, formulae, or an E6B flight computer are used to calculate the effects of air density on aircraft rate of climb, rate of fuel burn, and airspeed. A course line is drawn on the aeronautical chart along with estimated positions at fixed intervals. Visual observations of ground features are used to obtain fixes. By comparing the fix and the estimated position, corrections are made to the aircraft's heading and ground speed. Dead reckoning is on the curriculum for VFR pilots worldwide. It is taught regardless of whether the aircraft has navigation aids such as GPS, ADF and VOR, and is an ICAO requirement. Many flying training schools will prevent a student from using electronic aids until they have mastered dead reckoning. Inertial navigation systems, which are nearly universal on more advanced aircraft, use dead reckoning internally. The INS provides reliable navigation capability under virtually any conditions, without the need for external navigation references, although it is still prone to slight errors. Automotive navigation. Dead reckoning is today implemented in some high-end automotive navigation systems in order to overcome the limitations of GPS/GNSS technology alone. Satellite microwave signals are unavailable in parking garages and tunnels. and often severely degraded in urban canyons and near trees due to blocked lines of sight to the satellites or multipath propagation. In a dead reckoning navigation system, the car is equipped with sensors that know the wheel circumference and record wheel rotations and steering direction. These sensors are often already present in cars for other purposes and can be read by the navigation system from the controller area network bus. The navigation system then uses a Kalman filter to integrate the always available sensor data with the accurate, but occasionally unavailable position information from the satellite data into a combined position fix. Autonomous navigation in robotics. Dead reckoning is utilized in some lower-end, non-mission critical, or tightly constrained by time or weight, robotic applications. It is usually used to reduce the need for sensing technology, such as ultrasonic sensors, GPS, or placement of some linear and rotary encoders in an autonomous robot, thus greatly reducing cost and complexity at the expense of performance and repeatability. The proper utilization of dead reckoning in this sense would be to supply a known percentage of electrical power or hydraulic pressure to the robot's drive motors over a given amount of time from a general starting point. Dead reckoning is not totally accurate, which can lead to errors in distance estimates ranging from a few millimeters to kilometers, based upon the duration of the run, the speed of the robot, the length of the run, and several other factors. Pedestrian dead reckoning (PED). With the increased sensor offering in smartphones, built-in accelerometers can be used as a pedometer, and built-in magnetometer as a compass heading provider. Pedestrian dead reckoning can be used to supplement other navigation methods in a similar way to automotive navigation, or to extend navigation into areas where other navigation systems are unavailable. In a simple implementation, the user holds their phone in front of them, and each step causes position to move forward a fixed distance in the direction measured by the compass. Accuracy is limited by the sensor precision, magnetic disturbances inside structures, and unknown variables such as carrying position and stride length. Another challenge is differentiating walking from running, and recognizing movements like bicycling, climbing stairs, or riding an elevator. Before phone-based systems existed, many custom PED systems existed. While a pedometer can only be used to measure linear distance traveled, PED systems have an embedded magnetometer for heading measurement. Custom PED systems can take many forms including special boots, belts, and watches, where the variability of carrying position has been minimized to better utilize magnetometer heading. True dead reckoning is fairly complicated, as it is not only important to minimize basic drift, but also to handle different carrying scenarios and movements, as well as hardware differences across phone models. Brought to you by WikiVidi Documentaries. Would you like to know more?